I have here three linear equations of four unknowns. And like the first video where I talked about reduced row echelon form and solving systems of linear equations using augmented matrices, at least my gut feeling says, look, I have fewer equations than variables, so I probably won't be able to constrain this enough. Or maybe I'll have an infinite number of solutions. But let's see if I'm right. So let's construct the augmented matrix for this system of equations. So my coefficients on the x1 terms are 1, 1, and 2. Coefficients on the x2 are 2, 2, and 4. 2, 2, and 4. Coefficients on the x3 are 1, 2, and 0. 1, 2, and 0. There's, of course, no x3 term, so we can view it as a 0 coefficient. Coefficients on the x4, 1, minus 1, and 6. 1, minus 1, and 6. And then on the right-hand side of the equal sign, I have 8, 12, and 4. 8, 12, and 4. There's my augmented matrix. Now let's put this guy into reduced row echelon form. So the first thing I want to do is I want to zero out these two rows right here. So what can we do? So I'm going to keep my first row the same for now. So it's 1, 2, 1, 1, 8. And that line essentially represents my equal sign. And if let's see, what I can do is let me replace the second row with the second row minus the first row. So 1 minus 1 is 0. 2 minus 2 is 0. 2 minus 1 is 1. Negative 1 minus 1 is minus 2. And then 12 minus 8 is 4. There you go. That looks good so far. It looks like column or x2, which is represented by column 2, looks like it might be a free variable, but we're not 100% sure yet. Let's do all of our rows. So to get rid of this guy right here, let's replace our third equation with our third equation minus 2 times our first equation. So we get 2 minus 2 times 1 is 0. 4 minus 2 times 2, well, that's 0. 0 minus 2 times 1, that's minus 2. 6 minus 2 times 1, well, that's 4, right? 6 minus 2. And then 4 minus 2 times 8. Minus 2 times 8 is minus 16. 4 minus 16 is minus 12. Minus 12. Now what can we do? Well, let's see if we can get rid of this minus 2 term right there. So let me rewrite my augmented matrix. I'm going to keep row 2 the same this time. So I get a 0, 0, 1, minus 2. Then essentially my equal sign, or the augmented part of the matrix. And now let's see what I can do. Well, actually, let me get rid of this 0 up here, because I want to get in a reduced row echelon form. So any of my pivot entries, which are always going to have the coefficient 1 or the entry 1, it should be the only non-zero term in my row. So how do I get rid of this one here? Well, I can replace row 1 with row 1 minus row 2. So 1 minus 0 is 1. 2 minus 0 is 2. 1 minus 1 is 0. 1 minus minus 2, that's 1 plus 2, which is 3. And then 8 minus 4 is 4. There you go. And now how can I get rid of this guy? Well, let me replace row 3 with row 3 plus 2 times row 1. With row 3 plus 2 times row 2, right? Because then you'd have minus 2 plus 2 times this, and they'd cancel out. So let's see. The zeros, 0 plus 2 times 0, that's 0. 0 plus 2 times 0, that's 0. Minus 2 plus 2 times 1 is 0. 4 plus 2 times minus 2, that's 4 minus 4, that's 0. And then I have minus 12 plus 2 times 4. That's minus 12 plus 8. That's minus 4. Minus 4. Now, this is interesting right now. This is interesting. I've essentially put this in reduced row echelon form. I have two pivot entries. That's a pivot entry right there. That's a pivot entry right there. They're the only non-zero term in their respective columns. This is just a kind of a style issue, but this pivot entry is in a lower row than that one, so it's to the right. It's in a column to the right of this one right there. And when I just inspect it, this looks like this column 2 looks kind of like a free variable. There's no pivot entry there, no pivot entry there. But let's see. Let's map this back to our system of equations. These are just numbers to me, and I just kind of mechanically, almost like a computer, put this in reduced row echelon form. Actually, almost exactly like a computer. But let me put it back to my system of linear equations to see what our result is. So we get 1 times x1. Let me write it in yellow. So I get 1 times x1 plus 2 times x2 plus 0 times x3 plus 3 times x4 is equal to 4. Obviously, I could ignore this term right there. I didn't even have to write it. Then, actually, I'm not going to write that. Then I get 0 times x1 plus 0 times x2 plus 1 times x3. So I could just write that. Well, I'll just write the 1. 1 times x3 minus 2 times x4 is equal to 4. And then this last term, what do I get? I get 0 x1 plus 0 x2 plus 0 x3 plus 0 x4. Well, all of that's equal to 0. And I've got to write something on the left-hand side. So let me just write a 0. And that's got to be equal to minus 4. Well, this doesn't make any sense whatsoever. 0 equals minus 4. This is a nonsensical constraint. This is impossible. 0 can never equal minus 4. This is impossible. This is impossible. Which means that it is essentially impossible to find an intersection of these three systems of equations, or a solution set that satisfies all of them. So when we looked at this initially at the beginning of the video, we said, oh, there's only 3 equations that have 4 unknowns. Maybe there's going to be an infinite set of solutions. But it turns out that these 3, I guess you can call them these 3 surfaces, don't intersect in R4, right? These are all 4-dimensional. We're dealing in R4 right here because we have, I guess each vector has 4 components, or we have 4 variables, I guess is the way you could think about it. And it's always hard to visualize things in R4. But if we were doing things in R3, we can imagine a situation where, let's say we had 2 planes in R3. So that's one plane right there. And then I had another completely parallel plane to that one. So I had another completely parallel plane to that first one. Even though these would be 2 planes in R3, so let me give an example. So let's say that this first plane was represented by the equation 3x plus 6y plus 9z is equal to 5. And the second plane was represented by the equation 3x plus 6y plus 9z is equal to 2. These 2 planes in R3, this is the case of R3, so this is R3 right here. These 2 planes, clearly they'll never intersect, because obviously this one has the same coefficients adding up to 5. This one has the same coefficients adding up to 2. And if we just looked at this initially, if it wasn't so obvious, we said, oh, we have only 2 equations with 3 unknowns. Maybe this has an infinite set of solutions. But it won't be the case, because you can actually just subtract this equation from the bottom equation from the top equation, and what do you get? You would get a very familiar. So if you just subtract the bottom equation from the top equation, you get 3x minus 3x, 6y minus 6y, 9z minus 9z. Actually, let me do it right here. So if that minus that, you get 0 is equal to 5 minus 2, which is 3, which is a very similar result that we got up there. So when you have 2 parallel planes, in this case in R3, or really do any kind of 2 parallel equations, or a set of parallel equations, they won't intersect, and you're going to get, when you either put in reduced row echelon form, or you just do basic elimination, or you solve the system, you're going to get a statement that 0 is equal to something. And that means that there are no solutions. No solutions. So the general takeaway, if you have 0 equals something, no solutions. If you have the same number of pivot variables, the same number of pivot entries as you do columns, so if you get the situations, let me write this down. This is good to know. If you have 0 is equal to anything, then that means no solution. If you're dealing in R3, you're probably dealing with parallel planes. In R2, you're dealing with parallel lines. If you have the situation where you have the same number of pivot entries as columns. So it's just, 1, 1, 1, 1, and it just, and this is the case of R4 maybe right there. I think you get the idea. That equals A, B, C, D. Then you have a unique solution. Now, if you have any free variables, so free variables look like this. So let's say I have 1, 0, 1, 0, and then I have the entry 1, 1. Let me be careful. 0. Let me do it like this. 1, 0, 0, and then I have the entry 1, 2, and then I have a bunch of zeros over here. And then this has to equal 0. Remember, if this was a bunch of zeros equaling some variable, then I would have no solution, or equaling some constant. But let's say this is equal to 5, this is equal to 2. If this is our reduced row echelon form that we eventually get to, then we have a few free variables. This is a free, or I guess we could call this column a free column to some degree. This one would be 2 because it has no pivot entries. Right? These are the pivot entries. So this is, let's say, variable x2, and that's variable x4. Then these will be free. We can set them equal to anything. So then here we have unlimited solutions, or no unique solutions. And that was actually the first example we saw. And these are really the three cases that you're going to see every time. And it's good to get familiar with them so you're never going to get stumped up when you have something like 0 equals -4 or 0 equals 3. Or if you have just a bunch of zeros in a bunch of rows. But I want to make that very clear. Sometimes you see a bunch of zeros here on the left-hand side of kind of the augmented divide. And you might say, oh, maybe I have no unique solution. I have an infinite number of solutions. But you got to look at this entry right here. If this whole thing is 0 and you have free variables, then you have an infinite number of solutions. If you have a statement like 0 is equal to a, if this is equal to 7 right here, then all of a sudden you would have no solution to this, that you're dealing with parallel surfaces. Anyway, hopefully you found that helpful.